So next we have to consider the base design values for laterally loaded connections. So let's recall, so we have value of z prime, which is equal to the adjustment factors multiplied by the base design value for laterally connected connectors z. So we have discussed earlier the different adjustment factors. However, the value z, as based on the yield limit model, is a function of the following parameters. First is the mode of failure. Next is the diameter of the fastener d, bearing length of the fastener L, specific gravity G, direction of loading, yield strength of fastener embedding Fy sub Yb, and dowel bearing strength. Okay, so we had different modes of failure. Currently we have here mode 1, which is a bearing failure. So it occurs when the connector crushes the wood member. So it can occur both in side members or in the main member. As you can see here in the figure, the wood is crushed here in the main member, while in this part the wood is crushed on the side member. So it can also happen during three wooden member connections, or three member connections. You can see here the wood in the main members crushed, and the wood in the side members were crushed. Okay. Next is the mode 2. So the connector pivots within the member, as you can see here. Localized crushing of the wood members, and it also occurs when the fastener does not yield, and it only occurs in single shear connections. Next we have mode 3. So the plastic hinge forms in the fastener. So one plastic hinge in single shear connection, as you can see here. This become the plastic hinge. Meanwhile, we have two plastic hinges for double shear. So it can also occur between on the main member and the side member. So you can see here, two hinges for double shear for three member connections. Next, the mode 4, wherein the two plastic hinges form in a single shear plane, as we can see here. We have here two plastic hinges form in a single shear plane, as you can see here, and limited localized crushing of the wood fibers near the shear planes. So as you can see here, two plastic hinges form in a single shear plane, as you can see here, this one and this one, for single shear and double shear respectively. So failure of connections on lateral loads is based on the crushing of wood and yielding of fasteners. Thus the dowel bearing strength F sub E and the yield strength of the fastener F sub YB. So we have here where the diameter D is less than 1/4 inch. We have a dowel bearing strength of 16,600 G raised to 1.84, and for diameters greater than 1/4 inches, we have here on dowel bearing strength F sub E parallel to the grain, which is equal to 11,200 G. And next is the dowel bearing strength perpendicular to the grain, which is 6,100 G raised to 1.5 over D over raised to 0.5. So where G is the specific gravity of the wood. Okay. Next, aside from the enumerated equation, so we have here the summarized values of F sub E values in NDS 11.3.2, table 11.3.2. So when connections are made with steel side plates, dowel bearing strength is given by F sub E is equals to 1.5 F sub U for hot rolled steel. Meanwhile, F sub E is equals to 1.375 FU for cold form steel. Next is the yield strength of fastener F sub YB is determined by test in accordance to ASTM F 1575 and F 606. So typical values are enumerated below. So per bolt and lag screw with the diameters less than 0.375 inches, you have F sub YB of 45,000 psi. And for common box or sinker nail, lag screw, wood screw, and which is from low to medium carbon steel. So we have their respective ranges of diameters and their respective yield strength of the fastener values. Okay. So as you can see here, we have the yield mode and their corresponding formula for the laterally loaded connectors per fastener. So we have your single shear and double shear. So we have here different values for the variables L sub m, F e sub m, R sub d, L sub s, F sub es, um, R sub e, R sub d. Okay, so for loading at an angle to grain of d greater than 1/4 inches, so use Hankinson formula. So F sub e theta is equals to F sub e parallel multiplied by F sub e perpendicular over F sub e parallel sine squared theta plus F sub e parallel perpendicular multiplied by cosine squared theta. Okay, so the values of the variables are here. So D is the diameter of the connector in inches. F sub YB is the dowel bending strength. P sub in terms of PSI from NDS table I1. R sub D is the reduction term, NDS table 11.3.1B or table 8.5. K theta is the 1 plus 0.25 multiplied by theta over 90 for R sub D. And R sub D is equal to F sub EM over F sub ES. R sub T is equal to L sub M over L sub S. L sub M is the main member of dowel length in inches, and L sub S is the side member dowel length in inches. Also, F sub EM is the main member dowel bearing strength PSI. F sub ES is the side member dowel bearing strength in PSI. And F sub EM or F sub ES is equals to F sub E for diameters less than 1/4 inches. So it is also equal to F sub E parallel or F sub E perpendicular for applied loads either in parallel or perpendicular to the grain. So F sub E theta is for applied loads at an angle to the grain. F sub M or F sub ES is equals to 87,000 psi for ASTM 836 steel side plates, 61,850 psi for ASTM A 653 steel side plates, and 7,500 psi for fastener embedded into concrete. So for lag screws, there are rules regarding their L sub M and D. Refer to NDES 11.3.4 to see the provision. So we have here the value for the K sub 1, K sub 2, and K sub 3. And the reduction factor table R sub D is this one. So if we were given the fastener size, as you can see here, we have the respective yield modes and their corresponding reduction factor value of R sub D. Okay. So for large diameter fasteners, different yield modes have different values for their reduction factor R sub D. For subtle problem 8.3, from the connection shown, determine the nominal lateral design value Z and compare the results from appropriate design in the NDS code. So lumber is spruce pine fir for main and side members, and nail is common. For sample problem number 3, we have here the based on the previous slide. So our required is to determine the lateral design value Z and compare the results to the appropriate table in the NDS code. Lumber is spruce pine fir for the main and side members, and the nail is common type. Okay. So we have here the dimension of the wooden members. So it is 2 inches by 4 inches. So for our solution, first we need to get the value of G of the spruce pine fir from NDS table 11.3.28. So as you can see here, we have value spruce pine fir of 0.42, and from NDS table L4 we need to get the details about the the nail, common nail. So as you can see here, you have the common nail and the required 8D. So for 8D, you have a length of 2.5 inches, length diameter of 0.131 inches, and diameter head of 0.266 inches. Okay, so now we need to get the details from table 8.4. As you can see here, so since you have a diameter of 0.131 inches, so based on the different what do you call this, groups, so our scenario, so we have our diameter fits right into here, 0.099, between 0.099 and 0.142, and it has a fastener yield strength of 100,000 psi. Now we need to get the value for D. So since our variable value for the variable D is 0.131 inches, which is less than 1/4 inch, so we have here the dowel bearing strength of 16,600 G raised to 1.84. Substituting this value of G based on the spruce pine fir of 0.42, we have here the value for the dowel bearing strength of 3,364 psi. Now we need to solve the ratio between the dowel bearing strength for the main member and side member, but since they are based on the same member as well as the same type of wood, so it has a ratio of 1. Meanwhile, R sub T is equal to L sub M over L sub S, or which is the depth of penetration of the nail, or rather the fastener to the member. So as you can see here, we have 2.5 inch by 1.5 over 1.5. So this value is equal to 1 inches, since the length of the nail D 8D is 2.5 inches, and based on the problem, the nail first passed through the side member, then pierced to the main member. So as you can see here, we have a value of 1.5, actual dimensions of 1.5 inches. Thus the remaining dimension here is equals to 2.5 inches minus 1.5 inch, which is 1 inch. Okay, so we have value 0.667. Now based on, you need to check the reduction factor R sub D from table 8.5. so since you have a value of D of less than 0.17, so for the yield modes, type 1 for the main, type 1 for the side, type 2, type 3 for the main, type 3 for the side, and type 4, we have an R sub D of 2.2. So using the values of the variables R sub E, R sub T, and R sub D, so you can see here we will get the value for K1. Substituting these values, we have value of 0.357. Using the equation to solve for K sub 2, we have here replacing this value, have here value of 1.241, and value for the equation for K sub 3. So substituting the variables will yield the value of 1.11. So now we need to calculate the value for Z for each mode of failure. So first is the mode 1M. Substituting these variables, D, L sub M, F, E sub M, and R sub D, we need to value of Z for mode 1 for the main member of 200.311 pounds. Next is the mode 1 for the side members. So replacing these values, variables also, we need to a value of 300.466 pounds. Next, for mode 2, replacing the value for the variables here, we have here the value of 107.226 pounds. And mode 3 main, so substituting this the variables, we yield to a value of 82.862 pounds. And mode sub 3 for the side members, so replacing also these variables, will yield to a value of 111.173. And last, for mode 4, using these equations, replacing the variables, we have value of 82.601 pounds. So the lowest value is 82.601 pounds. Therefore, value of Z is 82.601 pounds, which is comparable to the value of NDS in table 11N. So basing this value for table n, so we have here G equals to 0.42 for spruce pine fir, and we have here this side member thickness of 1.5 and diameter D, nail diameter 131 inches, which is 8D. That's a value of 82 pounds. Okay. So this table, so the table 11 and or the other similar table, so they're just for checking, okay, if your answer is correct. Next, for sample problem 4, we have here for the common connection shown, determine the nominal lateral design value Z perpendicular and compare the results from appropriate table in the NDS code. Lumber is hemisphere for the main member and the steel plates are 1/4 in inches A36 steel. So you have here load P perpendicular to the grain, and we have here thickness of the wood, which is 2.5 inches, and we have here a 1/4 inch plate, which is steel plate, which is A36 steel, and we have here P over which P over 2 is the tension on each steel plate, and we have here 3x main member, and last we have about in diameter of 5/8 inches. For sample problem 4, so you can see in the previous slide, we are required to determine the nominal lateral design value Z perpendicular and compare the results from the appropriate NDS table or NDS code. So lumber is hemisphere for the main member, and steel plates of 1/4 inch thickness are the side members, which are A36 steel. We are required to determine the nominal lateral design value Z perpendicular. So based from in this table 11.3.2a, the value of G for hemisphere is 0.43. Okay, so for the value of D, we have 5/8 inch bolt, so that will be the diameter, and the value of L sub M is equals to 2.5 inches. So as you can see here, since the thickness here is 2.5 inches. So from table 8.4, we have here a bolt based on the given figure, and we have a value of D greater than 0.375 since our diameter is 5/8. So we have a fastener yield strength of 45,000 psi. Now determining the double bearing strength for the main member, so this will be equal to the FE sub E perpendicular, which will equal to 6,100 G raised to 1.45 over D raised to 0.5. So substituting the values, you will arrive the value of F sub EM of 2,269 psi. The value for F sub ES is equals to 87,000 psi due to the A36 steel side plates, and the value of R sub E will be equal to 2269 over 87,000, which will yield to value of 0.026. For the value of R sub D, it will be equal to L sub M over L sub S. So since the bolt passed through the set to the main member and side members, so we have here the value of L sub M of 2.5 over the value of 0.25 for the L sub S, which is yield to the value of R sub T is equal to 10, and value of theta will be equal to 90 degrees since it will be the angle of the grain and the application of load is perpendicular. So from from the table 8.5, we need to determine the reduction factor R sub D. Since our value for D is between 0.25 and 1, since our diameter is 5/8 inches, so we can see here we need to we will consider the yield mode for the one yield mode for case 1 for the main member, and case 1 for the side member, as well as case 3 for the main member, case 3 for the side member, and case 4. So K0 will be equal to, using the formula from the slides, is equals to 1 plus 0.25 multiplied by theta over 90, which will yield to a value of 1.25. K sub 3 will be substituting the values of the variables in order to determine the value of K sub 3, which will be equal to 40.695. Now, we need to determine the value of Z for each mode failure. So, for mode 1 sub M, as you can see here, value of reduction factor R sub D of 4K K theta. So, you have here the value of K theta. So, substituting the values, we yield the value of Z for 709.0625. Also, for mode 1 sub S, so the reduction factor is still 4K theta. So, using the formula here, yield to value 5,437.5 pounds. So, mode 3 is not mode 2 is not applicable. Mode 3 is not applicable for the main member. Meanwhile, for the mode 3 for the side member, so R sub D is equals to 3.2 K0. So, substituting these values here, we yield to a value of 1,285.745 pounds. So, using the value of R sub mode 4, using the value of reduction factor R sub D of 3.2 K theta, substituting these values, it will lead to the value of 1,590.868 pounds. So, choosing the lowest value of R sub D is 709.0625 pounds. Therefore, Z perpendicular is equals to 709.0625 pounds, which gives to the value of NDST table 11G. Using this value, you have your 0.43 hemisphere and a bolt diameter of 5/8. So as you can see, we have the value of Z perpendicular of 700 pounds. Okay. For sample problem 5, for the knee brace connection shown, design the connection assuming 16D common nails. The wood species is spruce pine fir and is exposed to the weather. Loads are due to lateral wind. Okay, so we have here a P of 1,000 pounds. We have here 2" by 6" on each side of the wood with a 45 degrees angle from the horizontal axis, and we have here a 10" by 10" post. So this is the final design for the connections. So for sample problem number 5, we need to determine the number of 16D common nails to be used in order to resist the 1,000 pound load. So the wood species is spruce pine fir and is exposed to weather, and loads are due to lateral wind. Okay, so we have here a 10" by 10" post, and there is a 2" by 6" wood, which needs to be connected by 16D common nails. So we are tasked to determine the number of nails to be which will satisfy the loads. Okay, so first, from NDS table L sub 4, we have here the common nail and 16D. So we have here the dimensions for the 16D common nail, which has a length of 3.5 inch, a diameter of 0.162 inches. Okay. From NDS table 11.3.2a, we have here the specific gravity for the spruce pine fir wood species of 0.42, and from table 8.4, we have the value for the we have here the value for the fastener yield strength of 90,000 psi. Now we need to determine the dowel bearing strength. So we have here we have a diameter less than 0.25 inches. Thus, our dowel bearing strength is 16,600 G raised to 1.84, where G is the 0.42. Substituting the value, we have here the value of 3,364 psi. Now, using we need to determine R sub E, so we need to divide F sub EM over F sub ES, which is equal to 1, and we need to get the value of R sub T, which is equal to L sub M over L sub S, which is equal to 1.33. Okay. Now for table 8.5, we need to determine the reduction factor R sub D. Since our diameter is less than 0.17, we have here R sub D of 2.2. Now we need to solve for k sub 1, k sub 2, and k sub 3. So using the equation and substituting the variables, you have value k sub 1 of 0.4916457285. Determining the value of k sub 2 using the equation, we have the value of k sub 2 of 1.085920471, and value of k sub 3 using the equation and substituting the variables, we have here the value of 1.150375351. So now we need to calculate the value of C for each mode of failure. So mode of failure for mode 1 sub M. So we have here, using the equation, we have here the value of 495.25 pounds, 495.425 pounds. Mode sub 1S, we have here value of 371.569 pounds. Mode sub 2, we have here 182.663 pounds. Mode sub 3, we have here the value of 179.328 pounds. Mode sub 3S is equals to 142.484 pounds, and mode sub 4, we have a value of 119.838 pounds. So lowest value is 119.838 pounds, therefore Z is equals to 1.19.838 pounds, which is comparable to the value of NDS table 11N. So here's the value for NDS 11N. We have a value of 120 pounds. Okay. Now we need to determine the minimum distances from table 8.1. So as you can see, we have the end distance, tension parallel to the grain, edge distance, center to center with the load parallel to the grain, and gauge. We have here staggered inline. So we have here the values for the minimum for wood members without pre-bored holes. Okay. So computing this value, and from table 8.2, we have your nails. We have the minimum penetration for the main member, which is 10 inches. Sorry, rather 1.62 inches. So we now have the different values for the spacing as well as the penetration of the nails. So next is we need to determine the adjustment value. So for C sub M, we have here value of 0.7, since based on the problem it is exposed to weather. And next is lateral loads. Okay. C sub M. So C sub M is also 0.7 for fasteners with diameter less than 1/4 inches. Thus we will use this value. Okay. Next is that since we have here from table 2.3.2, we have here the wind load. So we have here the value of 1.6 for C sub D. Okay. So all other factors are 1.0. Getting the Z prime is equals to adjustment factors multiplied by the base design value for the capacity of the fastener. So we have here an adjusted value of 134.219 pounds. Now we need to require the number of we now need to determine the number of nails. So we have 1,000 pounds over the capacity per nail. So we have the value of 8 nails. Okay. So you can set your own connection configuration as long as the minimum spacing requirements are met. Okay. For the base design value of the withdrawal loaded connectors, so for the withdrawal loaded connectors, for the variable W, so we can solve it using one of these three equations. So we have here different equations for different fastener types. So for die screws, we will use the equation of 1800 G raised to 3 halves multiplied by D raised to 3 fourths. For wood screws, we have here the value of, the equation of 2850 G squared multiplied by D. And last is for nails, which has the equation of 1380 G raised to 5 halves multiplied by D, where W is the withdrawal design value, pounds per inch of penetration, and G is the specific gravity of the wood. D, on the other hand, is the fastener diameter. So with sample problem number 6, with reference to the figure below, determine the allowable P max for the following connector types. A, for 3/8-inch lag screw. B, for number 12 wood screw. C, for 16D common nail. And so the wood member experiences normal temperature and moisture conditions supply, and C sub D is equals to 1.64 wind. Lumber is hemisphere. Okay. So sample problem number 6, we have here we need to determine the P max for the different connector types. So for A, we have 3-inch lag screw. B, number 12 wood screw. And C, 16D common nail. So normal temperature and moisture condition supply, and C sub D is equals to 1.64 wind, and the lumber is hemisphere. Okay, so based on NDS code 11.3.2a, we have here the value of hemisphere of 0.43, and using 3/8-inch lag screw, so substituting the value for G and D, so we have here the value of 243.23 pounds per inch. Okay, which agrees to the NDS code table 11.2a, so 243. So the next is we need to adjust it for penetration. So since the values given for W is pounds per inch, then we need to get the total penetration load that it can handle. So multiplying by 3, since we have here 3 inches of penetration, so we have here the value of 729.66 pounds. Now adjusting the values based on the given load conditions, so our capacity for P max will be equal to 1967.456 pounds. Next is for wood screw, number 12 wood screw. As you can see here, have your diameter of 0.216 inches. So using the formula, W is equal to 2850 G squared D. So substituting the value, we have here the value of 113.824 pounds per inch. So which agrees to the value of NDS code 11.2b, 114. And adjusting for penetration, so multiplying by the depth of penetration 3 inches, we have here adjusted value for W of adjusted for penetration of 341.472 pounds. Now adjusting it due to the given load conditions and adjustment factors, so we have here value of 546.3552 pounds. Next is the 16D common nail. So using the NDS table N4, we have D is equals to 0.62 inches. As you can see here, 0.162, and using the formula 1380 G raised to 5 halves multiplied by D, we have here the value of 27 pounds per inch. So which agrees to the value of NDS code table 11.2c. As you can see, 27. Now adjusting for penetration multiplied by the depth of penetration of 3 inches, you have here the adjusted value W of 81 pounds, and adjusting to the P max is equals to multiplying by the adjustment factors, we have here the value of 129.6 pounds. So for combined and lateral, for combined lateral and withdrawal loads, so we have here the value Z prime alpha, which is equal to this equation, W prime multiplied by P multiplied by Z prime over W prime P cosine squared alpha plus Z prime sine squared alpha for lag screws and wood screws, And for nails, we have the equation of W prime multiplied by P multiplied by Z prime over W prime P cosine alpha plus Z prime sine alpha for nails, where Z prime alpha is the adjusted resulting sine value under loaded combined loading. W prime is the adjusted withdrawal design value. P is the length of penetration into the main member in inches. Z prime is the adjusted lateral design value. And alpha is the angle between the wood surface and in direction of the load applied.